In this video, we will deal with two problems, both involving blocks that are colliding and that are separated by springs. Okay. So in the first problem, there is a mass m1 that's traveling towards the right, and it collides with a mass m2 that is attached to a spring. Okay, and the spring is restrained by a rigid surface. Both these masses are sliding on frictionless surfaces. So energy here is conserved. Okay, so now the question is, when the blocks stop momentarily, okay, what is the compression of the spring? Okay, so let's do this. Uh, uh, During the collision, okay, so what would happen here is that this mass moves to the right and it uh, touches this mass, m2, but doesn't stick to it, but they both move together. Okay, so now what happens here is that if we write the equation for conservation of momentum, m1 v1 equals m1 plus m2 times the velocity with which both masses are moving together just after the collision. So v here equals m1 v1 divided by m1 plus m2. Okay, this is what happens during the collision process. So after the collision, we have a situation where both these masses, they stick together, okay, and they come to rest. Okay, they come to rest momentarily. So we want to find the compression of the spring in that situation. So here the energy is conserved. So the kinetic energy of the blocks, okay, uh, together, this is after the collision, equals the potential energy of the spring, okay, of the spring at the maximum compression plus the kinetic energy of the blocks, at final compression. Okay? At final compression. So since we know that these blocks are at rest, the kinetic energy of blocks is actually zero. Okay, so let's proceed. So the kinetic energy of the blocks is nothing but half m1 plus m2 times v square, and that equals half kx squared. Okay, so uh, what we get here is, if we plug in the value of v, if we plug that in, we will get x equal to m1 plus m2 divided by k to the power half times v. Okay, okay. Essentially, so that equals, okay, so that equals m1 plus m2 divided by k to the power half, and we plug in the value of capital V, that is m1 v1 divided by m1 plus m2. Okay, so so that here turns out to be about square root of 6 divided by 10 meters. Okay, so that's the value of compression, okay, when both these masses have stopped moving. Okay, so that's pretty easy to solve. Okay, so just to reprise the problem, so we applied the law of conservation of momentum to begin with to find the velocity of the two blocks moving together. Then we applied the law of conservation of energy, It is possible because there are no dissipation or dissipative forces here. So what we do is we cancel out the halves and we find that x equals m1 plus m2 divided by k raised to the square root times v, and we plug in the value of v and we do the math and we find that x equals square root over 6 over 10 meters. Okay, so let's move over into a slightly different problem. Okay, so here the situation is that uh, there is a block of mass m1 that is moving at a high speed, and it collides with a block of mass m2 which is bigger, but that's moving slower. Okay, and the first block is moving at a speed of 10 meters per second, the second block is moving at a speed of 5 meters per second. Okay, and the spring constant here, which I didn't mention, the spring constant here equals 1120 newtons per meter. Okay, so we want to find the compression of the spring at the instant the two masses have the same velocity. So here, so what we do is that we apply the law of conservation of momentum. Okay, so when the two masses have the same velocity, okay, the total momentum is equal to what they had before. So the momentum that was there earlier is m1 v1 plus m2 v2, and that equals the final momentum. Okay, this is m1 plus m2 times v. Okay, and where v is the velocity of both masses moving together. So here we get v equals m1 v1 plus m2 v2 divided by m1 plus m2. Okay, so one of the things that does also happen is that the energy is conserved. Okay, so the energy is conserved because there are no dissipative forces here. Okay, so we can write the conservation of energy as half m1 v1 square plus half m2 v2 square equals half m1 plus m2 times v square, okay, plus half kx square. Okay, so here it is. So here the what we can do very easily is let the halves cancel out. Okay, so we basically we write m1 v1 square plus m2 v2 square, okay, equals m1 plus m2 times m1 v1 plus m2 v2 square divided by m1 plus m2 square, okay, plus kx square. Okay. So what we do here is that we plug in the values. Okay, is essentially this is 2 kilograms times 10 square plus 5 kilograms times 3 square, where 3 is the velocity, initial velocity of mass v2, m1 plus m2. Okay, essentially is let's see, 2 times 10 plus 5 times 3 square, and so we've simplified this a little bit, divided by m1 plus m2, that is 5 plus 2. Okay, because what happens here is that one of these m1 plus m2 cancels out, so we are just left with m1 plus m2 here. Plus 1120 times kx times x squared, right? So x here, okay, equals basically 245 minus 175 divided by 1120. Okay, half equals 0.25 meters. Okay, so that's pretty simple. So although this sounds like a hard problem, so what we did was Okay, so we use the law of conservation of momentum to find the final velocity of these two blocks since they were moving together. Then we use the law of conservation of energy, okay, to equate the initial sum of energies, the kinetic energies, to the to the sum of the final kinetic energy of the blocks plus the potential energy of the spring. So, and we simplified it, okay, plugged in the values and found uh, the compression of the spring. So you can see that these problems are relatively simple to solve, provided we apply the right concepts. Okay. So if you like this video, please click on the like button and subscribe to this channel for further updates. Thank you.